Yes, good afternoon, students. We were discussing about the chemical bonding chapter. Chemical bonding chapter. We were discussing about the chemical bonding chapter. In the chemical bonding chapter, formation of covalent bond already we have studied, and Lewis cell structure also we have studied. Now we are going to study how to calculate the formal charge on a polyatomic ion. On a polyatomic ion, or for the molecule, how to calculate the formal charge. So to calculate the formal charge, see, this will be asking for 1 mark for your final examination, for your NCERT examination. It will be asking for 1 mark. Formal charge is equal to number of valence electrons minus number of lone pair of electrons minus half into number of bond pair electrons. So, number of valence electrons minus number of lone pair of electrons minus half into number of bond pair of electrons. So, this is the formula to calculate the formal charge. Let me give an example. Carbon dioxide. Calculate the formal charge on the carbon atom and on the oxygen atom in the carbon dioxide. You need to calculate it. So, according to the formula, first, if you are calculating the formal charge on the carbon atom, C is equal to number of valence electrons. How many number of valence electrons are present? 4 minus number of lone pair of electrons. How many lone pair of electrons are present? 0 minus half into number of bond pairs of electrons. 4 pairs are bond. 4 means 8 electrons. So it is equal to 0. See, making this carbon dioxide, first you need to write the Lewis dot structure. In the carbon dioxide, we are writing the Lewis structure as CO2 will be like this, and on the oxygen atom 2 lone pair of electron. See, using this you can calculate the formal charge. See, without knowing the Lewis dot structure, you cannot calculate the formal charge. See, the formal charge on the carbon atom, number of valence electron is 4 for the carbon atom, minus number of lone pair of electrons on the carbon atom is 0. See, these two are the bonded pair of electron, into minus half into number of bond pair of electrons on the carbon atom. So total 8 electrons is present. 4 pairs, 8 electrons, so that is equal to 0. This one we have calculated for the oxygen atom. Next, if you consider one oxygen atom, consider this is the first oxygen atom, this one is the second oxygen atom. Now you need to calculate the charge, formal charge on the first oxygen atom. So first oxygen atom is equal to number of valence electrons is 6. 2 unpaired electrons, 4 paired electrons. I mean 2 lone pair of electron and 2 unpaired electrons are present. So total 6 minus number of lone pair of electron on the oxygen atom is 1 to 2 pairs of electrons. 2 pairs of electron is nothing but the 4 minus half into number of bonded pairs electrons. How many bond pairs? 2 pairs of electrons. 2 pairs of electrons is present. So 2 pairs is nothing but 4 electron. 4 electron, isn't it? So it becomes 0. 6 minus 6. 6 minus 6 is equal to 0. Next, for the second oxygen atom, second oxygen atom, if you calculate it with the same way, 6 minus 4 minus half into 4 equal to 0. So there is no formal charge on the oxygen atom as well as on the carbon atom in the carbon dioxide. Let me take another example. NO2 minus. NO2 minus, if you write the Lewis dot structure, 1, 2, 1, 2, 3, 4, 5, 6. So total 2 bonds. Next, between the oxygen and the nitrogen, single bond. 1, 2, 3, 4, 5, 6. And on the nitrogen atom, 2 lone pair of electron. One paired electron. So this oxygen carries a negative charge because excess number of the electron is present on the oxygen atom. Here also the same number of electron is present, but the bonded pair actually it has to form 2 bond pairs, but it is forming only 1 bond pair. That's why this one oxygen getting the negative charge. Excess concentration of the electron present on the oxygen atom, so it is getting the negative charge. Here there is no charge, but we need to calculate the formal charge on the nitrogen atom as well as on the oxygen atom. Now, calculating the formal charge on the nitrogen atom, N is equal to valence electrons for the nitrogen is 5 minus how many this one lone pair of electron 2. So this one is a lone pair of electron minus half into how many bonded pair of electron 1, 2, 3. So 3 pairs 6 electrons. 3 pairs 6 electrons. So there is no charge on the nitrogen atom, isn't it? Next, if you consider this one is the first oxygen atom, this one is the second oxygen atom. If you are calculating the formal charge on the oxygen atom, first oxygen atom is equal to this one. Valence electrons for the oxygen atom is 6 valence electrons minus lone pair of electron on this oxygen atom is 6, isn't it? 2 plus 2 plus 2, 6 minus half into how many electrons are as bonded electrons? 1 pair, it is 2, isn't it? So it is nothing but a minus 1 charge. Next, for the second oxygen atom, if you calculate it, second oxygen atom formal charge is 6 minus 4. 2 lone pair of electrons, so total 4 electrons minus half into 2 plus 2. Total 4 electrons, 2 bonded electrons, bond pair of electrons. It is nothing but 4 electrons. Total it is equal to 0. It is equal to 0. So, this oxygen atom no charge, nitrogen atom no charge, only on the oxygen atom there will be a charge. So, this will be asking for one more question for the NCERT part. Calculate the formal charge, nitrogen or oxygen or carbon. So, whatever it may be, we can ask it. Another example, CO3 2 minus. This CO3 2 minus, you can write it as C double bond O, single bond O, single bond O, lone pair of electron on the oxygen atom, 3 each, 6 electrons, 1, 2, 3, 4. So this is the structure of a carbonate ion according to the Lewis dot structure. According to the Lewis dot structure, carbonate ion structure is like this. Now you need to calculate the charge on the carbon atom. Charge on the carbon atom. Consider this one is the first oxygen atom, second oxygen atom and the third oxygen atom. Carbon, formal charge on the carbon atom is equal to 4 minus 0 minus half into 8, isn't it? So total 8 bonded electrons are there, bond pairs of electron 1, 2, 3, 4, 4 into 2, 8 electrons is equal to 0 charge on the carbon atom. Next, if you calculate for the first oxygen atom, If you calculate it for the first oxygen atom 6 minus valence electrons on the oxygen atom is 6 minus number of paired electron is 4 minus half into 2 bonded paired electrons. So half into 4 is equal to 0. That is for the first carbon atom. Next, second and the third is one and the same, isn't it? So let us calculate with the same procedure for the second and the third oxygen atom. So 6 minus 6, isn't it? 6 minus 6. 6 is the valence electrons. 6 is the valence electrons. 6 is paired lone pair of electron minus half into 2 is equal to minus 1 is equal to minus 1. So second oxygen atom as well as the third oxygen atom, second oxygen atom as well as the third oxygen atom have got the minus 1 charge. So if you want to rewrite this formula, we write it over here. Oxygen 1, 2, 3, 4, 5, 6 minus 1 charge. Oxygen atom 1, 2, 3, 4, 5, 6 and double bond O 1, 2, 3, 4. Hope the structure is clear. I think Puneet is messaging this structure you cannot visible, and so I am writing the same structure over here. And the calculation part is one and the same as like we have calculated for the nitrogen and for the carbon dioxide. So we are getting the 2 minus charge on the carbonate ion. So you are writing as CO3 2 minus, CO3 2 minus, because 2 minus 1 charge for the 2 oxygen atoms, so minus 2 charge. I hope it's clear calculating the formal charge. It's important for the first question as well as the second question, how to calculate the charge on the ion. For the competitive part also, next let me give 2-3 examples as homework problem. To take it as a homework problem. Calculate the formal charge on the O3, calculate the formal charge on the carbon monoxide, carbon as well as oxygen you need to calculate it. Next, to calculate the formal charge in H2SO4. Please go through the problem, calculate the number of electrons which is present in it. You need to calculate, take it as a homework problem. Next, write on the side heading as a bond parameters. Bond parameters. Bond parameters are nothing but, see, before explaining about the bond parameters, let me continue with the bond parameters only. Bond parameters are nothing but the bond measurements. How can we measure the bonds in the covalent bond as well as in the ionic bond? We know that during the formation of the molecule, atoms within the molecules are arranged in a regular manner. Whatever it may be the molecule, if you consider the H2O molecule, one H2O molecule, another H2O molecule, between the oxygen and the hydrogen, distance will be one and the same. So that distance between the oxygen and the hydrogen and the bond angle, I mean the arrangement, geometry of the molecule will be one and the same, whatever it may be the water molecule. Now, so these measurements for the bonds within the molecule itself is called as a bond parameters. First one, to calculate or to explain the bond parameters is bond enthalpy. Bond enthalpy. See, this bond enthalpy term already have studied in the thermodynamics topic. Bond enthalpy is nothing but it is the change in enthalpy when one mole of a bond get break. It forms its atoms in their ground state. It is nothing but a bond enthalpy. Bond enthalpy is nothing but the energies. It is a change in enthalpy when one mole of a bond get break. It forms its atoms is called as a bond enthalpy. Now let me explain the bond energy. Bond energy. Okay, bond energy is nothing but, say, we know that during the formation of the molecule, either energy will be released or energy will be gained for the formation of the molecule. During the formation of the molecule, energy will be released or energy will be gained. The same molecule, if we get break, if we break it, we will be getting the atoms. See, during breaking of that molecule, that bond, energy may be released or energy may be required. So the bond energy is nothing but it is the energy required or energy is released when one mole of a bond is formed or break. It is the energy released or absorbed when one mole of the bond is formed or get break. So if the energy is released during the formation of the bond, energy get required to break that bond. So energy released or energy required to break one mole of a bond or to make one mole of a bond is nothing but the bond energy. Important note is the bond energy. It is the energy required or released to make a bond or to break a bond. It is nothing but the bond energy. And this bond energy is mainly depends upon the atomic size of an atom present in the molecule. Atomic size of an atom present in the molecule. It is nothing but it's like we know that across the period atomic size decreases, down the group atomic size increases. If the bond is formed between the two smaller atoms and with the two bigger atoms, bigger atomic size. When the atomic size increases, bond energy decreases. When the atomic size is smaller, bond energy is more. Smaller the atomic size, higher the bond energy. Larger the atomic size, smaller the bond energy. Another factor is number of bonds which is present between the atoms. Number of bonds. We know that between the atoms maybe single bond, maybe double bond or maybe triple bond is present, isn't it? Single bond, double bond or the triple bond. Breaking of the single bond is easy than the double bond than the triple bond, isn't it? It's like the bond formation like this: single bond, double bond and the triple bond. Making this, breaking this bond is easy than if it is present with the double bond, difficult. If it is present as a triple bond, still more difficult to break this bond. So energy required to break three bonds is more than the double bond, than the single bond. It depends upon the number of bonds which is present in between the atoms. Second parameter is bond length. Bond length. Bond length is nothing but the distance between the center of the nucleus of one atom into another atom within the molecule is nothing but the bond length. Distance between the two nucleus of an atom in the molecule is nothing but the bond length. Bond length. Okay, distance between the two nucleus of an atom in the molecule is nothing but the bond length. And this bond length again it depends upon the atomic size. It depends upon the atomic size. It depends upon the atomic size. Smaller the atomic size, bond length is smaller one. Bigger the atomic size, larger is the larger is the length. So it depends upon the it depends upon the size of an atom. When the size of an atom is a smaller one, bond length between the atoms are lesser one. When the size of an atom is bigger one, bond length between the atom is larger one. Third factor to calculate or to explain the bond parameter is bond angle. Bond angle. See, during the formation of the molecule, atoms are arranged in the molecule with the different way. Atoms are arranged in the molecule with the different way. Either the molecule atoms, if you are considering, these two atoms are bonding with each other, means it will be present like this. Some distance will be present. Why this distance occurs? That is due to the electron repulsion between one atom to another atom. We know that at the center nucleus is present, electrons are revolving around the nucleus, so that repulsion in this electron, and the electron which is present in that this atom with the electrons which is present in this atom get repelled with each other, so that atoms are arranged with the regular manner with definite geometry. So while arranging the atoms within the molecule, it shows some angle between the atoms arrangement. Okay, so that is nothing but the bond angle formation. Best example for the this one bond angle is H2 molecule. In the hydrogen, H is arranged like this. We cannot write the bond angle. If I take an example of H2, see this one is a linear molecule. In case of H2O, oxygen is present at the center, hydrogen is present at the two ends. And we are writing the bent-like structure because of the presence of lone pair of electron and the bond pair of electron on the oxygen atom. So it is HOH is nothing but the bond angle of water. HOH is the bond angle of the water. Due to the repulsion between the electrons present within the molecule. See, these electrons are nothing but the bond pair electron and the lone pair of electron. I hope it's clear. See, this one is a lone pair of electron, this one is a bond pair of electron. Between these two some repulsion will be present. So that we are writing the H2 as like this, not like this, isn't it? We are not writing like this because within that hydrogen atom some repulsion will be present. So that repulsion makes the bond angle more. So these are the bond parameters to find the bond length as well as the bond energy as well as the bond angle. Next, ionic bond. Ionic bond. See, this ionic bond definition already have studied in your lower class. Ionic bond is nothing but the complete transfer of one or more electron from one valence atom into the valence shell of one atom into the valence shell of another atom is nothing but the ionic bond formation. See, this definition already have studied. So using this definition, one more thing you need to study. See, while the formation of the bond or during the formation of the bond, octet rule should be attained. Octet rule should be attained in the sense, if an atom loses the electron, it also attains the octet electronic configuration. Another atom gains the electron, that atom also attains the octet electronic configuration. Let me take a simple example, formation of sodium chloride, NaCl, sodium chloride formation. We know that we know that atomic number of sodium is 11. We are writing the electronic configuration as 1s2, 2s2, 2p6, 3s1. 1s2, 2s2, 2p6, 3s1. And 3s1 is considered as an valence shell of sodium atom. Another chlorine atom, atomic number is 17. 1s2, 2s2, 2p6, 3s2, 3p5, and 3s2, 3p5 is considered as a valence shell. If sodium, if it loses one electron, it becomes a 3s0 electronic configuration. And the inner shell is NH2NP6, isn't it? And the second example, that is second element, is chlorine. If it gains one electron, the electronic configuration becomes 3s2, 3p6. After gaining one electron, 3s2, 3p6, it attains the 3s0 electronic configuration, isn't it? So it also attains the the octet electronic configuration. Sodium as well as the chlorine also attains the octet electronic configuration. So this one you can write it as sodium, when it loses one electron, it forms Na plus ion. Chlorine, when it gains the electron, it forms Cl minus ion. It forms a sodium chloride. During the formation of sodium chloride, sodium attains the octet electronic configuration as well as the chlorine also attains the octet electronic configuration. So that sodium chloride we are considering as a stable molecule. Let me take another example, formation of calcium fluoride. Electronic configuration, the atomic number of the calcium is 20. So electronic configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6 and 4s2. 4s2 is considered as a valence shell, isn't it? And fluorine, 1s2, 2s2, 2p5. 2s2, 2p5 is considered as a valence shell, isn't it? When the calcium loses the electron, 2 electrons in its valence shell, it becomes 4s0 electronic configuration. If it gains the electron, it becomes 2s2, 2p6. This is for one fluorine atom. Another fluorine atom, it against 2s2, 2p6. 2s2, 2p6. So it also attains the octet electronic configuration. Now, if you write the molecule Ca2 plus 2F minus give rise to CaF2. Calcium fluoride structure is a stable one because calcium also attains octet electronic configuration. By losing the electron, fluorine attains octet electronic configuration by gaining the electron. And formation of the ionic bond, it depends upon the electronegativity character. It's like if the group 1 metals and the group 2 metals, most of the times group 1 metals, group 2 metals, when it is combining with the group 17 elements, it forming the ionic bond, because group 1 and group 2 metals are considered as an electropositive one, group 17 elements we are considering as an electronegative element. So most electropositive, most electronegative, and most electropositive is nothing but it is ready to give the electron. Most electronegative is nothing but it is ready to gain the electron. So electropositive one and electronegative one, it forms a ionic bond. So condition is electropositivity character or the electronegativity character. Electropositivity character and the electronegativity character. These two are the main factors which shows the ionic bond. Next, one more term I need to explain. Lattice energy or the lattice enthalpy. Lattice energy is nothing but it is the energy required to break a 1 mole of ionic crystal into its gaseous atoms. Gaseous atoms of the which again gaseous ions will be forming. when sodium chloride crystal is break, it forms Na plus ion and Cl minus ion, and this Na plus ion present in the gaseous state, Cl minus ion present in the gaseous state. So lattice energy is nothing but it is the energy required to break one mole of ionic crystal into its ions in their gaseous state. Now into its gaseous ions is nothing but the lattice energy. See, using the lattice energy we have explained about the Born-Haber cycle. Born-Haber cycle. See, this Born-Haber cycle in detail you have studied in the thermodynamics chapter. Formation of sodium to Na plus ion, formation of chlorine to chlorine atom to Cl minus ion, so that Na plus ion plus Cl minus ion give rise to NaCl in the solid state. So it is nothing but the Born-Haber cycle for the formation of sodium chloride. The same thing is repeating in the chemical bonding topic also. So Born-Haber cycle, if they ask in the exam, you can write the answer whatever you have written for the thermodynamics chapter, Born-Haber cycle. Same thing you can explain it over here also. And I am not going to explain it back, Born-Haber cycle, because already in detail I have explained in the thermodynamics chapter. Go through that Born-Haber cycle again and understand it very well. And this lattice energy again it is depends upon the size factor, isn't it? It depends upon the size factor. Greater the size, greater the atom, the cation and the anionic size, lesser the lattice energy. Smaller the size, greater the lattice energy. So that is about the lattice energy and the ionic bond. Next is drawback of or the limitations of octet rule. We have studied about the octet rule in the first class itself, isn't it? Limitations of octet rule. See, according to the octet rule, during the formation of the molecule, see this octet rule is explained using in the Lewis-Cossel electronic theory, isn't it? According to them, during the formation of the molecule, an atom present in the molecule has to get the octet electronic configuration. Then only that molecule is considered as a stable one. So that these atoms combining with another element. I said in the first class itself, for about 118 elements are present. Out of that, noble gases will not be reacting with one another, but other elements always present in the combined state. Why these elements are present in the combined state? It is mainly due to attain the octet electronic configuration. But some of the drawbacks are there too. Explain the octet rule in few of the molecules. So the first drawback or the first limitation of the octet rule is, see, when group 1 element, group 2 element and group 13th element. Group 1 element, group 2 elements and the group 13th element. So when it is combining with the other elements, it will not attain the octet rule. Best example, formation of lithium chloride, beryllium chloride, BeCl2 अथवा boron chloride or BF3 formation. In these examples, if you look at the electronic configuration of the lithium, not the chlorine I am saying, lithium, because lithium is a group 1 element, beryllium is a group 2 element, boron is a group 13 element. Outermost electronic configuration is this one is 1s2 Only I am writing the outermost electronic configuration. 2s1. This one is 2s2. This one is 3p1. Isn't it? 3p1. I mean 2s2, 3p1. During the formation of lithium chloride crystal, lithium chloride molecule, lithium loses 1 electron. So it attains only 1s2 electronic configuration. Then beryllium again 1s2 while forming the barrier. This one beryllium chloride. When it is forming the boron trichloride, again it is attaining 1s2 electronic configuration, isn't it? So it is not attaining the octet rule. Second rule says that in some of the molecules like phosphorus pentafluoride athava iodine hexafluoride as well as SF5. Let me take only 2 examples is also sufficient. SF5, SF6, not the SF5, SF6 formation. In these examples, this one center atom is a phosphorus, here it is iodine, here it is sulfur. During the sharing of electron between the fluorine and the phosphorus, one fluorine atom loses the electron, phosphorus gains the electron. Okay. Sorry, phosphorus loses electron, fluorine gains the electron. Totally 10 electrons will be present around the atom. Only 8 electrons instead of 8 to 10 electrons. Here 14 electrons are present around the iodine atom. Here 12 electrons are present around the sulfur atom while forming the SF6. So here 10 electrons, 14 electrons and the 12 electrons. Actually how much should be there? Only the 8 electrons should be there. Instead of that, more than that number of electrons will be present. So it breaks the octet. Third point. See, we said that noble gases will not be combining with any other elements in the periodic table. Still xenon and the krypton are the 2 noble gases combining with the, like fluorine, it forms xenon tetrafluoride, xenon oxyfluoride, krypton difluoride is formed. So these molecules are also exist. So the octet rule, rule get break because these are noble gases already which has been attained, but here it is forming the molecule. Even shape of the molecule or the geometry of the molecule. Shape of the molecule or the geometry of the molecule was not explained in the octet rule. Only just they said that total number of electrons around an atom during the formation of the molecule should be 8. Other than that, how overlapping will be taking place, how the shape of the molecules will be different, that thing nothing was explained in the octet rule. So it is the limitations of octet rule. Next, development of valence bond theory. Valence bond theory. VBT. Octet rule is based on the Lewis-Cossel structure. But advanced one, to improve the Lewis-Cossel structure, one more theory was introduced by the Sidgwick scientist name. So during the formation of, when we are writing the dot structure, overlapping of atomic orbital taking place. Bond formation is taking place between the elements. Bare electrons annu matra represent maduvanthadalla, even a bond is formed between the elements. So that bond formation is explained using the valence bond theory. Only the electrons which is present in the valence shell are involved in the bonding formation. So it is said that it is an valence bond theory. So according to the valence bond theory, some of the postulates are mentioned. According to the valence bond theory, the atom which is undergoing for the formation of the bond, that atom containing the valence shell, that valence shell containing the unpaired electrons. It contains the unpaired electrons, and these unpaired electrons orbitals almost have got similar energy. Unpaired electrons with the similar energy, it will be present, and these similar energy orbitals undergo overlapping. It forms with the lower energy bonded orbitals will be forming. So this one is explained using the valence bond theory. Atomic orbital should containing the unpaired electrons and similar energy, and these similar energy orbitals undergoing the overlapping. So according to the valence bond theory, after the overlapping, covalent bond is formed. During the covalent bond formation, it forms two kinds of the covalent bond. One is sigma bond, another one is a pi bond. Sigma bond and the pi bonds are the two covalent bonds. Now let us study how sigma bond is formed and how pi bond is formed by the overlapping of valence orbital of an atom. First one, formation of sigma bond by SS overlapping. Formation of sigma bond by SS overlapping. SS overlapping is nothing but S orbital spherical in shape, another S orbital spherical in shape. It undergo overlapping like this. So this one is overlapping. S orbital, it forms the sigma bond, SS overlapping. Let me take an example for the formation of SS overlapping with the sigma bond. Example for the SS overlapping, formation of a hydrogen molecule. See, this hydrogen molecule is formed. Let us write the electronic configuration. It's 1s1 for the one hydrogen atom, another hydrogen atom 1s1. S orbital I am writing as the spherical in shape. 1s orbital of one hydrogen atom, another 1s orbital of another hydrogen atom, undergo overlapping. It forms overlapping like this. Actually, ಎರಡು circle equal size ಅಲ್ಲಿ ಇರಬೇಕು. By drawing, it forms the sigma bond. It is nothing but H2 molecule formation. SS overlapping. Second type, formation of sigma bond by sp overlapping. sp overlapping will be taking place. One is s orbital, p orbital is dumbbell shape. It forms like this. So this overlapping is nothing but the sp overlapping. It forms a sigma bond. Example for the sp overlapping, formation of hydrogen fluoride. Formation of hydrogen fluoride. 1s1 and fluorine is 7. Sorry, fluorine is 9. Fluorine is 9. 1s2, 2s2, 2p5. I mean 7 electrons which will be present in the valence shell, but after gaining 1 electron it attains the octave electronic configuration. It is nothing but 2p, x2, 2p, y2, 2p, z1. So this 2p, z1 containing unpaired electron, that unpaired electron overlap with the 1s1 orbital of the hydrogen. So circle in shape, 1s1 of hydrogen, dumbbell shape. It is the 2p, z1, 2p, z1 dumbbell shape. It overlaps axially. Overlapping will be like this. So it forms the sigma bond. Yes, p overlapping, it forms a sigma bond. Pz orbital of don't write a 1. Pz orbital of fluorine atom undergoes overlapping, head-on overlapping, or axial overlapping. It forms a sigma bond. Now the third type is pp overlapping. It forms a sigma bond. pp overlapping, it forms a sigma bond. P orbital is nothing but the dumbbell shape. Again it is a dumbbell shape of one p orbital, another p orbital undergoes head-on overlapping. It forms sigma bond. It forms a sigma bond. Let me take an example. Formation of a fluorine molecule. Atomic number of the fluorine is 9. Electronic configuration becomes 1s2, 2s2, 2p5. 1s2, 2s2, 2p5. Here 2p5 is nothing but 2px2, 2pz1. See this 2pz1 is a dumbbell shape of one fluorine atom, another fluorine atom, another dumbbell shape. It overlaps, head-on overlapping. So this is the formation of a sigma bond. Formation of sigma bond taking place. Pz orbital of one fluorine atom, 2pz orbital of another fluorine atom. It forms the sigma bond. Next, fourth kind is pp overlapping, formation of a pi bond. pp overlapping, formation of the pi bond. pp overlapping, formation of the pi bond. Let me take an example. Let me write the axial diagram first, the orbital diagram first. Later on, we will take an example. During the formation of pp overlapping, for the formation of the pi bond, sideways overlapping taking place. One p orbital, another p orbital undergoes sideways overlapping. Sideways overlapping will be like this. It's like the p orbital is present like this. It forms a sideways overlapping and it forms a pi bond. And this pi bond is a weaker bond. It is a weaker bond because it is sideways overlapping. It is a sideways overlapping, so that it is a weaker bond. Let me take an example. Formation of a pi bond with the oxygen molecule. number, then writing the electronic configuration 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. This 2s2, 2p4 is nothing but 2p is 2, 2p1 and 2pz1. For one oxygen atom. Now let me show the px and the py orbital. Px and py orbital of another hydrogen atom. This one is a py. This one is a py and the pz. Py and the pz undergo overlapping. One is the axial overlapping, another one is the sideways overlapping. It forms a sigma bond, axial overlapping. It forms a pi bond, sigma bond, another one is a pi bond formation. Sigma bond and the pi bond formation. One sigma bond and one pi bond. One is head-on overlapping, another one is a sideways overlapping. Always pi bond is present with the sigma bond, but the sigma bond may or may not present with the pi bond. If the single bond is present within the molecule, all the bonds are the sigma bonds. If the double bond is present, one bond is a sigma bond, another bond is a pi bond. Okay. Next here. So these are about these are all about the names of the theory. Next is BSEPR theory. Valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. VSEPR theory. Valence shell electron pair repulsion theory. Within the name itself, electrons pair repulsion. Electron pair repulsion. See, due to the we know that in an atom, at the center nucleus is present, around this one nucleus electrons are revolving. During the bond formation, some distance will be present between the atoms within the molecule. That distance is due to the repulsion between the electrons. Isn't it? Repulsion between the electrons of one atom into the another atom. See, this due to the repulsion between the electrons of one atom to another atom, we can explain the valence shell electron pair repulsion theory. Because of this repulsion, we can explain the geometry of the molecule, as well as the shape of the molecule, as well as the bond angle of the molecule. We can explain that using the valence shell electron pair repulsion theory. Valence shell is nothing but the electrons which is present in the valence shell undergoing overlapping, formation of the covalent bond taking place. During the formation of the covalent bond, some repulsion will be taking place between the two terms. One is bond pair, another one is lone pair electron. Bond pair electron and the lone pair electron. Bond pair electron one is nothing but the bond pair electron. Sharing of the electron between the two atoms is nothing but the formation of the bond pair. Lone pair of electron is nothing but on the A atom, pair of electron is present. That pair of electron is nothing but the lone pair of electron. We know that lone pair of electron is negatively charged, as well as the bond pair of electron is also negatively charged, so that some repulsion will be taking place between the lone pair of electron and with the bond pair of electron. Due to that shape of the molecule will be differed with respect to the geometry. Geometry ಅಂತ ಹೇಳಿದ್ರೆ arrangement of the orbitals ಅನ್ನು ಹೇಳುವಂತದ್ದು. Shape of the molecule is nothing but after the lone pair bond pair repulsion, how exactly the elements which is present in the molecule, that arrangement is the shape of the molecule. So the shape of the molecule and geometry of the molecule, sometimes it will be same, sometimes it will be get differed. So geometry of the molecule, shape of the molecule, bond angle, as well as the lone pair concept and the bond pair concept is explained in the VSEPR theory, valence shell electron pair repulsion theory. Here the postulates is this only. So whatever I have explained, these are nothing but the postulates of VSEPR theory. This will be asking for the 3 marks in the final examination, as well as like for the test also we used to ask write the postulates of VSEPR theory. VSEPR theory nearly 3 to 4 postulates are there. That 3 to 4 postulates also includes all these points. Bond angle equal to lone pair, bond pair, as well as the geometry of the molecule, shape of the molecule, everything will be explained in the valence shell electron pair repulsion theory. So according to this, according to this, if two bond pairs are present, geometry of the molecule is linear. Linear is the geometry, and bond angle is if I consider A, B, 2, between A is present at the center, B is present at the 2 ends, so that it is present linearly, and the bond angle is 180 degree. If 3 bond pairs are present, geometry of the molecule is trigonal planar. If I take an example as AB2, best example is AlCl3, aluminium chloride. For this one, his best example is BeCl2. Let me write the examples over here. BeCl2, AlCl2. In the AB3 kind, it contains the 3 bond pair of electron. It forms the trigonal planar structure. Trigonal planar structure is nothing but it's like a triangle structure. A is present at the center, and 3 B atoms are present at the corners of the trigonal. And the bond angle is for about 120 degree. It is for about 120 degree. If 4 bond pairs are present, geometry of the molecule is tetrahedral geometry, and the bond angle is it is of kind AB4. It is 109 degree 28 minutes. Best example is the formation of CH4. If 5 bond pairs are present, trigonal bipyramidal. Trigonal bipyramidal geometry. It is of AB 5 kind, 5 pairs of electrons. Trigonal bipyramidal structure is nothing but A is at the center and the trigonal above the plane and below the plane. So D, it will be like this. Okay, so it is of AB 5 kind. Next example is ECl5 formation. If 6 bond pairs are present, 6 bond pairs are present, hexagonal structure, hexagonal geometry, and it is of AB6 kind. Hexagonal geometry is like, it is like one above the plane, one below the plane will be almost slant positional barutte. It will be like this. Actually, idara madhye like bond angle ee reeti formation ella agutte. It will be like this. So it forms the hexagonal structure. This example is formation of SF6. So it is nothing but the formation of electron repulsion theory using the bond pairs. How can you write the geometry of the molecule? And these geometries are very important to explain one more time. So all these explanation, it is only for the bond pair of electron. If lone pair of electron is present, how the structure will be differed? How the structure will be differed, we need to study. If two bond pair and one lone pair of electron, if it is present, it is of kind A, B to L. A, B to L. According to the geometry, A, B to L is nothing but the trigonal geometry, isn't it? Trigonal geometry. But the arrangement of the atoms will be like this: A, B, and the lone pair of electron is present on the atom. So it is nothing but the bent-like structure. It forms a bent-like structure, and the best example is formation of sulfur dioxide. Formation of sulfur dioxide. If 3 bond pairs and 1 lone pair of electron is present, 3 bond pair, 1 lone pair of electron is present, it is of kind AB3L, 4 pairs. Total 4 pairs means the shape will be, not the shape, geometry will be tetrahedral, isn't it? Tetrahedral, 3 plus 1, so total 4 pairs, tetrahedral geometry. A, B, and lone pair of electron, and the shape of the molecule is pyramidal in shape, and the best example is formation of NH3. Another example, 2 bond pair of electron, 2 lone pair of electron. It is AB2N2. AB2N2, total 4 pairs of electron is present, so that the geometry becomes again it is a tetrahedral geometry. Tetrahedral geometry. A is at the center, B and lone pair of electron on the this one A atom. So the structure is a bent-like structure. Best example is H2O. H2O. This structure already has studied in the hydrogen topic. If 3 bond pair electron, 2 lone pair of electron. It is AB3N2. AB3N2. Total 5 pairs of electron. It forms trigonal pyramidal. Trigonal pyramidal. Here it forms T-shaped structure. A, B, B. One lone pair, another lone pair. Repulsion will be taking place, so it forms a T-shaped structure. It forms a T-shaped structure. Best example is ClF3 formation. The SF3 formation is also. Next, 4 bond pairs and 1 lone pair. 4 bond pairs and 1 lone pair. It is of kind AB4L. Again, it is an trigonal pyramidal structure, isn't it? Trigonal pyramidal structure. Where I am going to write it over here. 1, 2, 3, 4. And 1 lone pair on the A atom. It forms a seesaw structure. It forms a seesaw structure. So it is of different kinds of the geometry formation depends on how many lone pair of electron and the bond pair of electron. Geometry depends upon total number of paired electron. Shape of the molecule depends upon how many bond pairs are electron, how many lone pair of electron which is present in it, and these type of questions are important for the competitive part. If it is asking for the NCERT, it will be asking for 1 mark question. It's like write the structure of AB2L, or write the structure of AB2L2, or what is the geometry of AB3L kind, what is the shape of AB2L2. So that kind of questions will be asking for the NCERT, write the shape, but for the competitive part, it is important. So these are about the valence shell, electron pair, repulsion theory. See in your NCERT textbook, in the chemical bonding chapter, these SEPR structures given in the yellow color shaded sheet. Please go through that sheet. At least try to understand if the number of lone pair of electron, if it is increases, if it is decreases, how it will be affecting on the shape of the molecule. Geometry will be one and the same. It is depends upon how many number of pairs of electron. Pairs, the lone pair irli, bond pair irli, geometry will be fixed one, but the shape of the molecule depends upon the number of lone pairs of electron, number of bond pairs of electrons. Okay, thank you.